This is the lesson on audio signal analysis. We will try out a few basic audio analysis and processing methods in MATLAB. This includes various basic noise reduction and sound manipulation methods. Let's go to MATLAB and get started. One of the more basic sound signal manipulations is combining two different sounds. Let's revisit our two cosine signals that we defined in the previous lesson. We define a sampling frequency as 44,100 hertz. F1 will be our A note at 440 hertz. F2 will be our E note at 660 hertz. Our duration will be 5 seconds. We then define our time variable and our individual signals. So t will range from 0 in steps of 1 divided by fs to time big T. And our individual signals, y1 and y2, can be defined using cosines. Creating a combined sound is as simple as adding the two together. This works only when the two signals have the same sampling frequency. If we want to combine two signals that have different sampling frequencies, one of them needs to be resampled to match the sampling frequency of the other signal first. Next, we can display the signal by plotting it and zooming in on the first 5 cycles of the signal. Next, let's listen to the sounds. First, Y1. Now, Y2. Since Y2 has a higher frequency, it creates a higher pitched sound. Finally, the combined sound. We can really hear both tones in the combined sound. What happens if we were to change the sampling frequency that we provide to sound SC? Let's play Y2 at the actual sampling frequency, and then Y1 at Fs multiplied by 660 over 440. Do you hear the difference? There is no difference at all in the pitch. How can that be? We know Y2 and Y1 are two different cosines. When we increase the sampling rate provided to sound SC, it plays signal Y1 at a faster rate. Instead of 44,100 samples per second, 66,150 samples are played every second. This effectively increases the frequencies in Y1 by a factor of 1.5, which makes our 440 Hz cosine have the same pitch as a 660 Hz cosine. In fact, Y1 becomes a 660 Hz cosine when we adjust the sampling rate. The only difference now between the two sounds is that Y1 is shorter in duration. When played at a faster rate, the sound finishes more quickly. Instead of 5 seconds, it is now 3.33 seconds. Let's try some of the same stuff with some audio samples in MATLAB, rather than the simple pure tones we have created. MATLAB has a number of different useful audio samples we can play with. Audio file input and output can be done with MATLAB's audio read and audio rate functions. Many common formats like MP3 and WAV are supported. Let's load an MP3 file. First, we load it into array YFD. We use audio read to load a sample called Funky Drums. This is a sample of drums that has been recorded at a sampling rate of 44,100 hertz. Next, we load a sample of ambient street noise, which we will call YST. The sampling rate for this file is 96,000 hertz. We want to combine the two signals, but with different sampling rates, we cannot just add them together directly. We first need to resample one. Let's resample YST to a 44.1 kilohertz rate. We can do this through interpolation with interp1. So we'll call this YST resamp. Using interp1, our time variable for YST in 96 kilohertz is defined as a vector ranging from 0 in steps of 1 over FSST to length YST minus 1. Divided by FSST. We're interpolating the values out of YST at times t. Okay, now let's listen to the sounds. First, the street sample. Then, the funky drums sample. But note that this sample is 25 seconds long. So instead of playing the whole thing, we'll play just the first part that corresponds to the first 5 seconds defined in time t. So we have a clean drum sample and an outdoor noise sample. Let's synthesize a new sound that sounds like someone is playing drums in a park. We do this now by simply adding the two signals together. Now, that sounds like we recorded an outdoor drum solo, even though these are two completely independent audio samples. Next, let's investigate the effect of sampling frequency. We can load a rock drum sample that has a 44.1 kilohertz sampling rate. It sounds like this. Now, if we play it again and double the sampling frequency, We speed it up by a factor of 2. Now it sounds like we have a superhuman drummer punk rock drum solo. A common concern with signals in general, including audio signals, is noise. Noise can be introduced into a signal in many different ways, typically during non-ideal transmission. We often want to try to recover a noise-free signal, or at least reduce the noise. Often, the quality of a signal is quantified in terms of signal-to-noise ratio. That is the ratio between the power of the signal relative to the power of the noise. Now that we know how to combine sounds using addition, we can investigate effects of additive noise. That is, noise that is added to the signal. The most common noise distribution is called white noise. This is additive, normally distributed, random noise with zero mean and finite standard deviation. It could not be easier to generate white noise in MATLAB. First, we define our standard deviation for our noise distribution, traditionally termed sigma, and seed our random number generator. Then we define our white noise as sigma multiplied by normally distributed random numbers in an array the size of our signal y. We can show the white noise signal in a plot. First, we move our two-tone signal y plot to a subplot. Then in the second subplot, we can show our noise. In our title, we can label it as being white noise. With sigma equal to a printout of our sigma variable. As we can see in the plot, our noise has magnitude much smaller than our signal, with maxima around 0.02 as opposed to the maxima around 2 in our signal. But the shape of the waveform is random. What does it sound like? Well, let's listen to it. You may have heard white noise before. It sounds like static on an old analog TV, or someone saying shh. Now let's corrupt our signal with this noise and see what it sounds like. Because the sigma we chose is small, the values in W noise are small relative to Y, so our signal-to-noise ratio is relatively high. This means that our signal dominates the sound, and the noise is relatively quiet, although still audible in the sound. Now let's try to create another type of noise to stimulate a crackling effect that is a common type of noise we would hear on an old vinyl record. This is called salt and pepper noise. Salt and pepper noise includes very brief popping noises that can be simulated with intermittent spikes in the signal. First, we choose how much salt and pepper we want. I'm going to choose a frequency of 10 hertz for about 10 crackles per second. Then we can write code to create our salt and pepper noise. Let's put it in a function. A function will take as inputs the salt and pepper rate, our time vector t, and sampling rate fs. We randomly pick indices at which to place the salt and pepper. So first, we initialize our salt and pepper noise vector to be zeros, the size of our input vector t. And then we can obtain randomly ordered indices into this vector. These indices can be created by getting the sorted indices of a list of random numbers and then keeping only the first set of indices corresponding to our specified salt and pepper rate. So that we get indices randomly distributed over the course of the signal with an average density of 10 locations per second of sound. For each of these indices, we will define the value in SP noise to be a normally distributed random number. This process will create an average of 10 crackles per second, each with random magnitude and randomly distributed over the course of the sound. Before using the function, we initialize our random number generator, and then we can call it. We can see what it is like in a plot. And we can listen to it. We can add it to our signal along with our low-level white noise. And this will really give us that old vinyl record effect. Let's try it with a sample of a guitar rather than a simple pure tone. This guitar sample is a 96 kilohertz sampled signal. So we first resample to our 44.1 kilohertz sampling rate. First, our time variable. Then the first channel of our signal, followed by our resample times. We can also plot it. Plotting it and focusing on a small subsection, we can see that this signal is far more complex than the sum of two cosines. Musical instruments do not create single pure tones, but rather a broad spectrum of frequencies with resonations and many harmonics, giving them a much richer sound than basic pure tones. Okay, we can create a vinyl version of this sample by adding our salt and pepper noise to it. First, let's listen to the clean version. And now the noisy version. That's good enough that some might even believe it really did come from vinyl. Another type of noise is often used in rock music called distortion. Almost all guitar amplifiers have a distortion effect option, and this effect provides a very distinctive rock and roll sound. Distortion occurs when a sound is passed through an amplifier with overdriven gain. The effect is that the amplifier gets saturated. That is, we have met and exceeded its maximum possible amplifier output. This distorts the signal in a highly nonlinear way. A non-saturated amplifier will simply scale the input signal by some gain factor A. But when the amplifier is saturated at some maximum value, we will call clip. Only values of the signal with magnitude less than clip divided by A are correctly scaled by A. Values of the signal with magnitude greater than clip divided by A are clipped to have a magnitude equal to clip, the maximum output of the amplifier. So basically, distortion just involves clipping the maximum magnitude of the signal. We can easily simulate this in MATLAB. First, let's find the maximum magnitude of our clean guitar signal as max. To distort this signal, we will clip it to a maximum magnitude equal to 10% of the max value in the signal. We initialize the distortion signal to be equal to the clean signal. Then we find values greater than clip and set them equal to clip. Likewise, for values less than minus clip, we set these equal to minus clip. Then we can listen to the sounds. First, the clean. Then the distorted. We definitely get that rock and roll distortion effect. In summary, in this lesson, we've looked at several ways to manipulate sounds in MATLAB. These are just a few of infinite possible procedures that you can dream up and code in MATLAB to manipulate sound signals.